In this lesson, you will learn to use channels to communicate between parallel sections of code without forcing an order of execution. There are several reasons why you might need parallel loops. First, you need parallel loops to run independent, parallel operations. You also need parallel loops to perform pipeline data processing. In addition, you need parallel loops if the application has multiple processes that need to execute at different loop rates. In this example, the top loop has a sample rate of 1000 Hz and reads 1000 samples each iteration, so this loop executes once every second. The middle loop executes once every 2 seconds, and the bottom loop executes once every 5 seconds. In LabVIEW, the flow of data, rather than the sequential order of commands, determines the execution order of block diagram elements. In common applications, you need to have multiple parallel running tasks. A challenge in programming parallel tasks is passing data among multiple loops without creating a data dependency. You cannot pass the data among parallel loops using a regular wire. If you pass the data using a regular wire, the loops are no longer parallel. Let's run this VI and examine what happens when we're trying to share data among parallel loops with a wire. We have two loops, producer loop and consumer loop, and we are trying to share the data of the random number function between these loops. Note that the consumer loop does not execute until it receives all its data inputs. The producer loop does not pass data out of the loop until the loop stops. So the consumer loop must wait for the value of the random number function, which is available only when the producer loop finishes. These loops do not execute in parallel. Channel wires operate differently from data flow wires. Channels allow transfer of data between the loops running in parallel without forcing an order of execution. Let's explore how to use channels to pass data between parallel loops. Channels are asynchronous connections. They allow data to be transferred between two sections of code running in parallel. Data enters the write VI and moves across to the read VI without creating a data dependency between the two loops. Channels allow the use of a single stop button to stop several loops. A channel wire expresses an asynchronous communication between two parallel sections of code without forcing an execution order. Every channel must have at least two endpoints, a writer and a reader. Endpoints are places in the code that exchange data. Writer endpoints write data into the channel. Reader endpoints read data out of the channel. You enable asynchronous data communication between parallel sections of code by connecting the writer endpoint to the reader endpoint. Note, channels do not create tunnels as they enter or leave a loop. This visually reinforces that the wire does not create a data flow dependency. Channels can accept any data type found in LabVIEW, for example, Boolean, numeric, waveform, cluster, array, object, string. The color of the channel wire indicates the data type of the channel. Channel endpoints do not appear in the palette. You create them by using the right-click menu on terminals and selecting the channel template that you would like to use. LabVIEW provides several channel templates. Choose the channel template to use based on your application needs. To create a channel, create a writer endpoint first. Right-click the data element and select Create Channel Writer from the shortcut menu. The second step is creating a reader endpoint. Right-click the output for the writer endpoint and select Create Channel Reader from the shortcut menu. You can use the abort capability of channels to stop multiple parallel loops with one stop button. Either endpoint of the channel can initiate the abort signal. In this example, either button will stop both loops immediately, dropping any buffered data. The last element signal allows the producer to stop and then the consumer to continue until buffered data is consumed. Use this option if you need to process all buffered samples. Here are some caveats and recommendations for using channels. Do not connect loops with a combination of regular wires and channel wires. This may result in the application hanging. Channels are not data and cannot be put into data containers, such as clusters, arrays, or data value references. There are different ways to communicate data between parallel loops. The first is stream communication. This is when you want to continuously transfer every point of data from one loop to another. For example, you might acquire data in one loop and transfer every point of acquisition data to a second loop to process or log. The second way of communicating data between loops is tag communication. This is when you want to share only the latest value. For example, a loop might only want to know the latest value of a stop button, or only the latest set point value. The third way is message communication. This is when you transfer messages between loops, and each message might also include message data that can use the most appropriate data type. For example, every time a user clicks a Process Data button, the application can send a message that includes the data to process to a separate processing loop. There are additional channels that you can experiment with: the accumulator tag, high-speed stream, lossy stream, one-element stream, and event messenger. Stream channels buffer and transfer data elements with no data loss from a single writer to a single reader. Channels can use a lot of memory for buffering if the producer loop consistently runs faster than the consumer loop. The buffered data will grow until LabVIEW eventually runs out of memory and crashes. You can set the size of the buffer on the right endpoint to limit the buffer. The right endpoint writes an element to a stream channel. The endpoint waits if the channel is full. The read endpoint reads an element from a stream channel. The endpoint waits if the channel is empty. Note, the channel size initializes on the first call of the writer endpoint. After that, the endpoint ignores the size input. Use the count output of the endpoint to get information about the buffered data elements. The count output returns the number of elements in the channel after the endpoint updates the channel. A channel is initialized when the block diagram it's on begins running. A channel closes when the last element input of the writer endpoint is true. If a channel closes, it ignores further writes to the channel. The reader endpoint continues reading data elements until the last element output of the reader endpoint returns true. This functionality can be used to stop multiple parallel loops with one stop button. The channel reinitializes when its calling block diagram begins another run. Communicating a stop signal with a stream channel is not recommended if the only data you are communicating is the stop signal. Using a stream channel for a stop signal can build a backlog in the channel if the writer runs faster than the reader. Use a tag channel instead for stop signal cases. Use a tag channel to share a single value among multiple readers and writers. Reader endpoints always read the latest value. Tag channels do not have buffering. Use the missed output of the reader endpoint to indicate the number of times that an element from the channel has been overwritten since the last read. If missed is 0, then the reader is reading a new value from the writer, and there is no missed data. If missed is -1, the reader is reading the same value as the last time. In this case, the writer has not written to the channel since the last read. A simple way to stop parallel loops with a single stop button is to do it with a tag channel. Use this only when there is no other data to communicate between the loops. Avoid using multiple channels to pass data between the same loops to avoid creating a deadlock or data integrity issues. A deadlock occurs when two parallel operations are both waiting on each other. Alpha cannot proceed until beta finishes, and beta cannot proceed until alpha finishes. When there are multiple channels, especially multiples of different types, each endpoint has different rules for how long it waits for data and what conditions make it stop. If those conditions occur for one endpoint, but not the other in the same loop, that loop may stop processing and stall the application. Likewise, it's easy to think that you are sending paired data through two channels and forget that the loops may process the data asynchronously, thus losing any pairing the sender intended. Use only one channel between any pair of loops to avoid these situations. It's best to have only one method of communicating between parallel operations. Use multiple methods of communication only when you need redundancy, like in the case of possible transmission errors over network communication. Use the messenger channel to transfer command-like messages. The messenger channel is capable of consolidating repetitive messages and disposing orphan messages when the channel aborts. The write endpoint writes a value to a messenger channel and blocks if the channel is full. The read endpoint waits to read a value from a messenger channel. If the wait for ACK input is true, the write endpoint will not complete until the message is acknowledged by the reader. You can use this input to synchronize the writer and reader loops. The ID output is a unique message number, which can be used to wait for an acknowledgement at a later time. Note, there is no last element input or output on the endpoints of a messenger channel because you can encode this feature as a message, and, in particular, there could be multiple messages that mean stop for different reasons. Use the Replace Channel Endpoint option from the shortcut menu of the channel endpoint to replace one channel template with another. Tag and messenger channel wires allow forks. With tag and messenger channels, you can have multiple writers and/or multiple readers. Stream channel wires do not allow forks. You can only have one reader and one writer endpoint. You can use Replicate Endpoint for stream channels. Replicate Endpoint duplicates a stream channel as two stream channels so that each of the readers of the channels get a separate copy of the data written into the original channel. The option to update the data type of a channel appears when the input is a different type, either a coercion dot or a completely unrelated type. Right-click the writer endpoint and choose Adapt to Element Type. You can also right-click the reader endpoint and choose Adapt to Channel Type. You can use a probe to debug a channel. Run your VI, then right-click the channel wire and choose Probe. This creates a special kind of probe for channels. Note, debugging capabilities are not available for high-speed stream channels. For detailed information about specific channel endpoints and their use, take the Channel Wire Communication online module. Unlike regular wires, you do not need to wire the channel in each frame of the case structure. You cannot wire a channel through a case structure or any other structure. Channel wires do not create a data flow connection, so wiring through these structures is meaningless. Channels can express some dynamic connections by using them with a call by reference node. Channels are not restricted to just the local block diagram. In this example, the sub-VI and the while loop begin executing at the same time and run in parallel. You can also use queues to transfer every point of data between parallel loops or VIs. Channels establish a static communication path within an application. In other words, a fixed number of channels and a fixed number of parties communicating on each channel. Channels support broadcast communication. On the other hand, queues can establish a dynamic communication path within an application. In other words, arbitrary communication paths can be decided at runtime between arbitrary number of communicants. Queues do not have broadcast communication. Instead, use notifiers. If you need to communicate data between parallel loops and you need to transfer every point of data, use queues. A queue can hold data of any type and can store multiple pieces of data. By default, queues work in a first-in, first-out manner, also known as FIFO. Therefore, the first element of data inserted or enqueued into the queue is the first element of data that is removed or dequeued from the queue. In LabVIEW, use the queue functions to create and use a queue for transferring every point of data between parallel loops in a VI, or even between different VIs. This diagram shows how you can use a queue. The producer loop adds elements to the queue, and the consumer loop removes elements from the queue. Click on each element of the VI to learn more about using queues. Let's set up this VI to wait 5,000 milliseconds each time an element is dequeued from the queue. This wait represents how long our processing algorithm on the dequeued element might take. What do you think will happen if you enqueue elements in this VI at a faster rate than you dequeue elements? Let's run the VI to find out what happens. As you can see, we are enqueuing elements at a faster rate than we are dequeuing elements. Notice that the number of the elements in the queue is increasing. Now let's stop enqueuing elements. Notice that the dequeued data comes out of the queue in the same order that the data was enqueued into the queue. Also, notice that the number of elements in the queue is now decreasing because we have stopped enqueuing elements, but the consumer loop is still dequeuing elements. Now let's click the Stop button. The producer loop exits, and the release queue function releases the queue. When the queue releases, the dequeue element function generates an error, which stops the consumer loop. This is just one way to handle releasing a queue. A buffer overflow error occurs when the application is not able to keep up with the hardware acquisition. Let's look at some examples of scenarios that can cause a buffer overflow error by either filling up the buffer too fast or emptying the buffer too slow. The following can contribute to filling up a buffer too fast. The following can contribute to emptying the buffer too slow. In this example, the loop uses the DAC-MX read VI to read from the DAC device buffer, and then it processes that data using a filter VI. To simulate different processing durations, we've added a wait function. The loop also uses a DAC-MX read property node to read the number of samples currently in the DAC device buffer. Now let's run the VI. Based on the sample rate of 1000 Hz and number of samples of 100, the loop will run 10 times per second and have a loop period of 100 milliseconds. Right now, the processing duration is minimal and the number of samples in the DAC buffer is low. Now I'll slowly increase the processing duration. By the time I increase the process duration to 100 milliseconds or more, I should notice that the number of samples left in the DAC buffer will continue to increase because the loop is no longer reading samples from the DAC buffer frequently enough. Eventually, the VI will return a buffer overflow error because the DAC buffer has a finite maximum number of samples it can hold. In this case, 10,000 samples is the most the buffer is configured to hold. To fix this problem, I can use one loop that's dedicated to just acquiring data, and use a queue to stream the acquired data to a second loop that's dedicated to processing the data. I also have a third loop that will display the number of elements currently stored in the queue. When I run this VI, the samples in DAC buffer indicator never goes above a certain number. This means that the acquisition loop is reading samples from the DAC buffer frequently enough. Now let's take a look at the number of elements in the queue. If this indicator is steadily increasing, that means that overall the VI is enqueuing elements at a faster rate than the VI is dequeuing elements from the queue. Therefore, the number of elements in the queue is growing over time. The number of elements in the queue will continue to grow until either the NQ rate becomes equal to or slower than the DQ rate. Although the number of elements in the queue is growing, the LabVIEW buffer for the queue is much larger than the DAC buffer, so the VI can hold a much greater number of samples before stopping. However, if the NQ rate remains faster than the DQ rate, the number of elements in the queue will continue to grow until LabVIEW eventually runs out of memory and crashes. Now I'll click the Stop Acquisition Loop. Notice that the VI continues to run. The number of elements in queue indicator now starts to decrease because the DQ element loop continues to remove elements from the queue and process them. Eventually, this loop will dequeue and process all the remaining elements. To speed this up, I'll decrease the process duration. Other ways of fixing a buffer overflow error include increasing the buffer size and reading the data more frequently. What if the number of elements in the queue keeps growing? Option 1. If the acquisition will eventually stop, then as long as the computer has enough memory to hold the maximum number of elements in the queue, then your VI will eventually finish processing all the elements in the queue after the acquisition stops. Option 2. If the acquisition is continuous, you can log all the data to file, then process the data at a later time by reading the data from the file. Variables have their use in LabVIEW. You can use local variables to update a display from multiple places in a diagram. You can use global variables as repositories for fixed constant data. Here are some things to keep in mind when using variables. Every time you read from a local or global variable, LabVIEW must make a full copy of your data. One copy of the data for the wire, and another to stay behind in the variable in case something else reads it. When you use wires, LabVIEW can track all the uses of a given value and optimize the data copies. Using variables for communication makes your diagram harder to read and debug. You will discover that finding all uses of a variable is much harder than following a wire downstream. Using variables for communication also opens the door to race conditions in your code, places where you get unintended, different results depending on which of the two pieces of parallel code execute first. These are the hardest types of bugs to debug in any programming language, so we encourage the use of safer communication methods. Here's a summary of what you've learned in this lesson.